In this video, we will work on the calibration step of the data reduction process. I'm still working with the Demetra 5.1 version, and this is the version dedicated to the LP600. I'm still working with the demonstration images. So I go to the manage observation. In the last videos, we worked out all the process up to the stacking operation. So now we will work on the calibration one. Calibration, this is one of the critical operations in the data reduction process. Okay, so the idea, of course, is that so far we have you see the result. If I see the result of my Vega image here, so I double click on the image and I can see the result in the bottom part of the screen. In this case, I see that the scale, the horizontal scale, is just pixels. Okay, so I know where are the pixels from my CCD sensors, but I don't know, for instance, this line, what is its wavelength. Okay, so the calibration operation is made to make the link between the pixel and the wavelengths. So at the end of this operation, we'll have the calibration here, the horizontal axis, which will be given in wavelengths, in physical wavelengths. To do that, of course, we use the calibration image here. So again, if I double click, I can see the profile here. And the idea is that we have taken, in same condition as the star, we have taken a calibration image. So a calibration image is an image in which we have some emission lines at a very well-known wavelengths. Okay, so you have many different emission lines, and Demetra will recognize these lines pattern, and it will be able to do the link between all these lines and the set of lines that is that are recorded, reference lines that are recorded in the system. So the normal usage of the calibration step is to work automatically, okay, because Demetra includes an automatic calibration tool that works fine and very quickly. So the normal usage is really to just select the automatic calibration and just run the images, okay, this way. Just click on this, and I have, so the result is we have some effects, some side effects at the beginning of the spectrum. This is a detail, and this is now the result of the calibration. So you see the first image is given in pixels horizontally, and if I click on the result, now I have a color scale, and now I have the different values, and especially I can see the Balmer lines that appear in the graph. That gives me a very good idea of the calibration quality. Okay, and you also have another result here, which is the R mass value. The R mass, in fact, is the gap, the total gap between the expected lines and the actual lines in the calibration image. So this value with the LP600, it should be below 0.5 angstroms. Okay, so it is 0.37 in this case. That is very good. It could be still lower, but when it is below 0.5, we consider that the calibration is correct. Okay, and of course I can do the same with the calibration image. So it could be strange to do the calibration of the calibration image, but it also gives an idea of the calibration operation. And in this case, if you double click on this image, then you can see which lines in the spectrum has been selected. Okay, and these lines are the reference lines in the software. Okay, so in this case, when you see that all these lines are properly detected and all these lines are appears on clear values, then it means it's fine. And by the way, this is here the yellow lines, very famous yellow line in the neon spectrum. Its wavelength is 5852 angstroms. I know that this is good calibration. Okay, so this is where everything works fine, which is most of the time. Okay, but now it may happen that the calibration is not good, so the error mass is not good, and you see in the Vega image, for instance, that your Balmer lines are not properly placed, properly detected. In this case, we'll open the calibration tool, but with the calibrate button, but we'll do that in the next video.